Okay, so some basic concepts that you should know, and I'm sure you do, very well from general chemistry, would be things like Lewis structures. I mean, that's all we do in this class is draw Lewis structures all day. Molecular geometry. I mean, you guys know when you're looking at something that is linear, tetrahedral, trigonal planar, all that good stuff. So those are important. I would also say ionic and covalent bonding. So ionic slash covalent bonding, formal charge. Again, this is something you guys can probably do in your sleep. Okay, just mentioning it. Okay, so you can. I know you guys know formal charges. Something that is really handy is in chapter 4, which was the acid basis chapter, or was it, sorry, maybe it was chapter 3 is the acids base chapter. But anyhow, if you remember the table of pKa's that we looked at, pKa's can really get you out of a jam in organic chemistry. So it's never a bad idea to look over pKa's because we cover them so much. And then I would also review, and I know you guys know how to assign RNS very well. So you all know the Kahn-Ingold pre-log rules better than I do probably. So you're very astute at determining RNS. But so make sure you review that if you're rusty on that. And we've done some practice on that. Just give me one sec here. So let's see here. Nomenclature. I mean, we cover a lot of nomenclature in this class. I mean, we learned how to name alkenes and alkynes and alkyl halides in organic one. And then in this class, we learned how to name everything: amides, carboxylic acids, acid chlorides, esters, all that good stuff. So nothing really new there. I'd make sure that you understand electrophile, electrophile versus nucleophile. Okay. Let's say I gave you two nucleophiles. Could you tell me which one is a stronger nucleophile? If I said hydroxide versus hydrosulfide, which one is a stronger nucleophile? Well, the hydrosulfide is a stronger nucleophile, right? Because it's more polarizable. It's a bigger atom. Sulfur is bigger than oxygen. It's in the third period. Okay. So I'd also tell you you should know things like SN1, SN1, SN2, E1, and E2 reactions. Those things never go away. So I'd make sure you know that. What else? The final exam always seems to have a question that involves the Williamson ether synthesis. So Williamson ether synthesis, that always shows up. Synthesis, okay? Very, very important. What else? Let's see here. So nothing really new there. Let's see. I would review the reactions from chapters 8 and 9. So 8 was the alkenes chapter, alkenes, and 9 was the alkynes chapter. And we use those reactions a lot in this class, so you're expected to know those, but just review those. What else? Diels-Alder is a reaction that always comes up on a final exam. It's a Nobel Prize winning reaction. Same thing with Grignard. Okay, huge reaction. I mean, we saw Grignard reagents how many times today? Like 10 times probably in one class. So super duper important. Then make sure you're able to assign a compound as being aromatic versus non-aromatic versus anti-aromatic. But a lot of the questions that are asked are just kind of, do you know when something is aromatic? Yes or no. Like which one of these is aromatic? Which one is, aromatic? That's it. Another name reaction that I think is really important in this class is Friedel-Crafts. Whether it's alkylation, or acylation. We used both of those reactions quite a bit in this class, so very, very important. Also, one that we went over, I think, 3 times today was the SNAR reaction, so you probably don't need to review that, but in case you think you do, it's an important reaction. One that we didn't cover today, but we covered in the electrophilic aromatic substitution chapter is elimination addition. And if you're like, what the heck is that? That's when we looked at benzyne. If you remember, we talked about benzyne for a hot minute. Make sure you understand that. Yeah, nothing really new there. And then just like Catherine brought up, electrophilic aromatic substitution, there's a lot to unpack there. There's just so many different reactions: nitration, sulfonation, alkylation, acylation, bromination, chlorination, but all those reactions are important, and you should understand, when you're dealing with an activator versus a deactivator, then whether it's strong, medium, or weak, right? All of that is going to be important. Another Nobel Prize winning reaction is the Wittig reaction. Okay, so Wittig reaction, a very, very important reaction in organic chemistry. Also, we talked about imines and enamines, and what those are used for, and how you make an imine and how you make an enamine. Also, acetals. Right, we spent a lot of time talking about acetals. We even used an acetal as a protecting group in Chemistry 3111. What else? So nomenclature, there's nothing really new there. So again, nothing new there, just synthesis. Let's see.
Will there also be epoxides?
For sure, yeah.
Okay.
Epoxides. Okay. There you go. So epoxides is definitely important. Remember, this is not an exhaustive list. Okay. This is just woodshedding some ideas of things that you would want to review. Okay. Let's see here. pKa's again. Oh, aldols. So aldol addition, right? Aldol addition, aldol condensation. We went over those in detail. So aldols, I mean, there's a whole chapter on, aldols, enols, enolates, enolates. Okay, those are all important, right? Like the Dieckmann cyclization that we looked at today. What else? Reductive amination. Reductive amination is a really important reaction. That would be from the amines chapter. We covered that in detail. Also, Hoffman elimination. If you remember, we went over the Hoffman elimination. We talked about Hoffman and Zaitsev in Organic 1, but in Organic 2, that's when we actually talk about the Hoffman elimination, where in the first step you use excess iodomethane, and then in the second step you use silver oxide as your base, and water and heat. Okay, so silver oxide. Anyhow, so Hoffman elimination is something that we covered. When it comes to sugars, so we did a whole chapter on carbohydrates, so D versus L. So you should understand when you're dealing with a D sugar, right? If you look at all the chiral centers, okay, it doesn't matter, right? Let's say you have an aldohexose. As long as the hydroxyl in the last chiral carbon is on the right-hand side, then it's a D sugar. If it's on the left-hand side, it's an L sugar. What else? You should be able to go from a Fisher projection, to a Haworth, or to go from a Fisher to a chair, or a Haworth to a chair, and back and forth, and all that kind of stuff. We went over that in detail. We talked about the what else? We talked about the Edmond degradation. We talked about we talked about Edmond degradation. We talked about Kiliani-Fisher synthesis, so chain lengthening, polymers. So polymers, I mean, that was chapter 27. That was, kind of blinked and you missed it sort of thing. And then spectroscopy, same kind of level as what we just looked at in the ACS study guide, that kind of thing. A little bit of proton, coupling, and carbon-13 and that kind of stuff. All right. So those are some of the major concepts that you want to review. But again, this is not an exhaustive list for the exam, but these are some ideas of things that you might want to take a look at.